Hi everyone, it's me again. I'm Gil Tene from Azul Systems, by the way, for those of you who don't know me, because there are no slides about that. I like to use this slide, by the way, as an opening slide for a lot of talks. It's a very good generic slide. Who here recognizes what that thing is? Wow, only you. And you've seen my previous talks. Really? Yep. That is the Apollo 13 CO2 scrubber. It's not the actual one, because that one probably burned out re-entry, but that's the one on the ground they practiced with. But I keep this in mind as this is the ultimate in duct tape engineering. It's this heroic feat that you get to do, and the kick people that actually achieved that must have gotten as amazing. But the thing to keep in mind whenever you look at that picture, our job, whenever that happens, is to make that never need to happen again. So most of the time when we find a lot of duct tape on stuff, the next thing to do is think of why the hell is it there and how can I keep it out of there? It's a little relevant to this, but we'll see. I actually think that the previous talk feeds very, very well into what we're going to talk about now. And a lot of the questions that came up about startup are relevant too. And one of the things that I think I'd like to ask people to change in how they think about the startup question has to do with a simple question. How many of you run programs only once? None of you? Yes, well, it's the bad programs, right? I don't really care about those startup times. Most of you don't. But assume for a minute that the program runs again and start thinking of what you do like a relay run. So what can we get across runs that can help us with these problems? Problems could be speed, problems could be startup, problems could be lots of things. And the minute you start thinking about that, then you look at what can I do that'll actually prime what we can do forward. So we can talk about, and there's some great efforts to reduce the work we do on startups so there'll be less of it. And then there's the how do we get that work done more quickly, and should we write optimized code that'll only run in the first 100 milliseconds so that later we replace it with other code, but we got to start up fast? What if we could learn from the previous run and use that information to make this run do something better, faster, quicker, whatever that is? So that's generally, when I talk about run-to-run information and the need to pass it around, that's the overall context and motivation. And the examples you can find for those that are probably concrete and easy to place have to do with things that benefit from that information crossing over. In many of these cases, the information we're looking for comes from our previous run. It could be a previous run right here. I ran it here, and now I'm running it here again. It could be a previous run that I ran in a canary deployment, put in a container and deployed to 1,000 things. It could be a previous run of something similar nearby, right? But somehow I want to get information from one run to another, and we could use that information for good. I'm not going to get too much into what are the goods. I'm going to go more into one of the challenges that we have with current JVMs and what could help with this information. That's really the subject for the talk. But let's take some motivating examples. A really simple one is class data sharing. Whether it's class data sharing just for the JDK or for application code, we're basically looking at eliminating some warm-up, startup, reducing some work, verification, loading of classes into data structures, that kind of stuff. Profile logging and replay, or priming of the JVM with a pre-primed profile is another example. Optimization code stashing, which is something what we call the ability to actually take JIT compiler output and next time I need it, not have to compute it. And then you could obviously think of AOT in this context as well. AOT is a form of cross-run information. Maybe the previous thing wasn't quite a run, but if you throw some PGO in there, you see why that could be a run. And there are many other examples we could look at. But I'll take a little detour to talk about speed. And in general, when we talk about startup and warm-up and all those, we often talk across each other. So I want my JVM to start up fast. What does that mean? For some people, it means I've got a GUI and I want to press a button. For some people, it means I want to start a Lambda or some function on a cloud, and I need it up quickly for the first response. But for some people, they mean I want the code to run fast. And not I need it quickly, but I need it fast. That's not the same thing. And when we look at speed in general, there are various aspects to speed. So for example, if you're doing continuous delivery, then every time you deploy cool code onto your nice array of cloud instances, you're causing tens or hundreds of thousands of slow operations to happen on a regular JVM because we're all going through that warm-up startup stuff. And this is not about quickness. You've got all the time in the world to roll them all over. They can take their time before they run into traffic. But they run into traffic slow, and they can't get away from the cars, whatever that is. Keep that analogy going. Other aspects of speed is just, are we fast when it's high load? Are we fast when it matters? If you want a nice money-making example, are we fast when the market opens? Nobody wants their first 10,000 trades to interpret and figure out how to do C1 compilation and then de-optimize 3 times before they settle. They want fast trades when the market opens, okay? And then within trading, there are 2 variations. There's, are you fast when you started, but there's also, are you fast when you actually trade? If you talk to people doing algo trading, then their job is basically to sit there and look at millions of things and knew nothing about them. And once in a while, they'll jump in and trade at 3 p.m. after a day full of not trading and being fully optimized to not trade. That's when they want to trade. Okay? So there are all kinds of aspects to this, of when does the speed matter, what kind of speed, and these are different things that pull in different directions often. And then, are we reliably fast, or if we run really fast, that happens sometimes. That doesn't need to be a crash, it could just be a meltdown. Right? A full de-opt of everything, because we have a bad assumption and now we can't handle the load. Okay, so speed would ideally look like this, but it doesn't look like that. In Java, speed looks like this. It kind of jumps up, and in the main context around that ramp looks like that. We start interpreted. We learn a little bit of the interpreted code. We pay attention. We put a profiling, low optimizing compiler on the first tier, collect more information, and then say, yeah, I know what to do about this, compile the hell out of it, get this nice blue code, but oops, we got it wrong, and we go back. And back and forth, those are the spikes. And eventually, you settle down on most of the hot code you're running is actually optimized. That's the good world we'd like to be in. And that means response time behaves like this over time. We start slow, and we get fast. Those spikes in the middle are the annoying other things JVMs do, like GC pauses. If we look at the overall picture, it looks like this over time. We start with really slow code, and then the code gets faster and faster. This is speed over time. And in general, when we look at this picture and want to improve it, there are multiple directions to improve it in. The 2 main ones that we're talking about when we think of run-to-run things are we want better JIT'ing, and we want to do the warm-up and startup and quickness thing better. We want to get to fast code faster, we want to start up faster, and we want to actually be faster, right? And these things are just garbage collection. They've got nothing to do with startup warm-up, but to complete the picture. Just a tiny little advertisement. When we think of it as Azul, we map our 3 features to that picture. We have a collector that takes out the spikes. We have a JIT compiler that keeps getting better at speed. And we have this ready now thing that's focused on the warm-up, startup, get that beginning thing going fast for the various motivations that there are. So in the motivating examples for why we want information across runs, we've got class data sharing, which I already talked about. You've got reduced footprint and improved load times. It does make things quicker. It doesn't make speed better, but it gets up off the ground faster, right? So it reduces cost. It's useful. Then if we take another example, there's like already now, or already now and others like it, the notion that we can record the profile from a successful previous run that actually did something we care about, and use that profile information to prime the next run, to make the profiles be there so we don't have to go through 1,000 interpreted loops and 10,000 C1 loops before we decide to do the first attempt at optimization that'll de-op 3 times. We can remember what the stable eventual optimization was and start there. in order to do that, we need information. So if we can start with a JVM that's primed and in this run, we don't have to go and repeat the optimize, deoptimize, because another run's already done it before and all the mistakes have been made in the past. We can try and run close to first speed on the first transaction. Now that, we actually segment the world into the people who care about the first transaction being fast and the people that just care about the second transaction being fast. It turns out that the first one is much harder to solve. You got to do initialization and all kinds of other things. If you're willing to let initialization happen before you actually kick speed in, and then maybe when I say second, it's not necessarily second, it's quickly after you start, but you can get there without forcing things to experience slowness in order to be fast. And basically, this kind of motivation hopefully is understood here, and it relies on information that came from previous runs. This is an example of the kind of impact we're talking about. You have the kind of the response time or time per transaction of the first run that just happens, and then you can see how a second run using the profile from the first run gets faster, and a third run actually going after that gets even better. This tends to settle down after 2 or 3 runs. And there's information that propagates from one to the other to make this happen. You want more motivation cases beyond just logging, profiling, and information. We could actually go and start looking at taking the actual hard work, hard lifting, heavy lifting of creating optimized code and trying to remember that so we don't have to compute it over and over again. And for that, we call that compile stashing. Imagine that the JIT could, given the exact same code with the exact same state, say, I know the answer. That's just caching, right? So if we had exactly the same situation, we could predetermine, or having predetermined before what this would be, use that information. And we do that today because we can actually stash stuff in a cache. And Ready Now will actually, when the profiles match, get a nice high hit rate, because we're running the same code, and if the profile is actually the same, and the state will be the same, we'll get the same question. And the nice thing is Ready Now actually kind of helps things have the same profile, because it tells them what the profile will be, and they usually actually listen to it. And then the last, more pie in the sky kind of motivating example is, imagine that your JIT was as a service. There are a few people here that have talked about that, including us. And the JIT is actually not in the JVM, but it's somewhere else. And that JIT basically gets questions for lots of JVMs. And the chances are that it's the same question over and over again for a few thousand methods, probably with similar profiles. So being able to cache that has obvious benefits, right? So these are motivating examples. So what's the problem, right? I mean, great, we're all going to build that. What problems do we have, and what actually happens, and what can we look at in things like HotSpot and OpenJDK today that are sort of in the way, and I'd like people to think about them as they build new things, especially code generators, okay? So all these things rely on us being able to repeat things run to run, otherwise we have no good information. And some of the things, like the code itself, tends to repeat run to run, but the things inside of the JVM, not so much, because the JVM's never had a reason to do this. The JVM generally just starts up with nothing, does whatever it wants, whatever it needs. It's doing it for itself, and it forgets everything when it's done. So we never had a motivation to cause the things we do to be repeatable. And we'll get into specific examples of things we do that are not repeatable here. So organically, these things break apart very quickly in most runs. So what are kind of examples we could use? One of them is class loaders. So class loaders have no name. And because they have no name, there's this problem with figuring what the hell the class loader I'm looking at here is, and how does it relate to the previous run. So we can have the exact same class loader with the exact same class. Everything we look at is the same, but they're doing something with that class and that method with a different profile. And if what we do is fall back to a common denominator profile that is the worst of all the classes, we lose a lot of stuff, right? So just simple examples like type specificity would be lost. But things like, there's this one place where you actually throw null pointer exceptions, but it's one out of the 100 class loaders you have. Do you really want all of them to compile without the optimizations? So what can we do about that? Class loaders are a bit of a mess. They don't have names semantically. But we can try and do some things. So for example, we could try and identify known loaders. There's this known thing. I know it's got a catalog number, and I can recognize it for what it is, and there are a few that we know. So the JDK itself has a few loaders we can identify because we know who they are. Just identifying them and setting them apart from the others is helpful because that at least lets us disambiguate some of the profiles or information about that. Then there's some other third-party things, like an OSGI container, kind of can figure out what that is, or some of the other common containers. We could probably figure them out and set them apart from the things that are not them. Now, within these, we still have the problem of what if that same container does 1,000 of the same, but at least it's that's problem. It's not Tomcat and the JDK both use the same class. What do I do about it? We can also try to auto-identify unknown things. Look for signatures. For example, we can look for things that are unique about a class loader. There's some class that only appears there. Or maybe there's some set of classes that as a set only appears there. There are ways to try and disambiguate and make the different loaders unique. And this could get interesting and very tricky. You could spend a whole bunch of time just on figuring out that space. But often it is worth it. We end up tackling this when we run into a place where this is a problem, so we try to figure out how to disambiguate for that place, but then slowly we build a repertoire of being able to disambiguate more and more of these things. So again, lots of work could be done on this path. Here's a useful thing we think actually could be useful in a future Java. How about if we give them names? What if they were willing to name their stuff? Just call a method that says that's the name, and then they call it again the next time, and now we can match them across the two runs. Yeah.
Technically, in 9, you have a name of a class loader.
What is the name?
You set it. As a user, you set it.
Oh yeah, that's what we're talking about. So if we add an API that lets the user set the name, we can use that name to match across runs. We actually added that API in Zing. We have customers that use it to match class loaders across runs to get, trading kind of profiling going. But yeah,
he's saying it's in 9.
Yeah.
There's an API in Java SE9 to do this.
There's a Java SE9 API to name a class loader?
Class loader has a third constructor that takes a string name, and you can even get it back.
That would be cool. I didn't know that, obviously. I got to check if we know that. But the thing about this is often you're not in control of that construction. Right? So the person wanting the thing and the person making the thing are not necessarily the same person or the same entity. And you're not going to mess with the container code that made this thing, but you want to tag it. So I think the late naming, we do late naming, kind of lazy binding name. And it does come in handy. And often these kind of problems will happen, if it was under your control, you would have done something about it. So I think if you could give it the name from the start, probably true too. But, I'll certainly look into that. Okay, so class loaders, disambiguating them, an API in a future JDK could help. Now let's look at class names and the contents of the class names. So, the program is exactly the same, but what we actually get to run in the JITs and stuff tends to be different. For example, reflection. It's this fun thing that happens every once in a while, and it's actually highly optimized in the JDK code to very lazily decide what to do if it gets hot, right? So initially you just do the reflection, but after it's run enough, we start auto-generating dereflectors for field access and construction or whatever it is we do hot with reflection. And those dereflectors are generated classes. Well, the generated classes will eventually get JITted because they're warm enough to have been generated. Presumably they'll keep getting warm, but their name is generated with a global counter. And that would be great if the order of warmness repeated every run, but it never does. Okay, so things do not get warm in exactly the same order, and you get one off and all the numbers are off. And if we tried to imagine that, we'll probably match wrong. So it blocks that. There's a really simple solution to that. We've implemented it for us. We think it'd be good for OpenJDK to do that, and that's to transition from counter-based or semi-random timing-based things to things that are more deterministic. For example, we can hash the name and the signature and stuff and get something that repeats run to run, and that comes out with some good results. Here's a warning. We ran into this for real in production. When you generate this, you want to generate a string, obviously in hex, right? Well, any number. Generating the string, in most of the ways you'll do that, might call locale. Locale calls reflections sometimes in some locales. And the result could be really fun in production. Okay. So this is blown up for us, for real. We fixed it. If somebody else attempts this, call us first. Okay. Reflection is one. Lambda Expressions. Lambda Expressions similarly generate code. They end up as generated code that didn't come into the JDK. It's generated by the JDK. And that name for that that's the naming of the actual generated code for the implementations. This is very similar to reflection, same counter problem, same solution applies. And then we have the Lambda forms, which are separately generated. And those are a little messier because they don't actually have names. But those also have solutions. Okay? The main motivation here is we'd like to be able to capture the thing about the class, record it, so the next time we see the same class with the same content, the same signature, we know something about it. There's a lot of value for everybody if we could do that. Other code generators, the XML Transform, we don't quite know why. Generates stuff that has exactly kind of the same names and the same signatures, but run to run the exact same XSLT generates slightly different bytecode. We haven't dug enough into it to figure out why, but that's annoying, So, hard to deal with. And then, plug in whatever code generator you have. And what I'm basically saying, if you're making code generators, try to think about this in a sense of give your things name that will hopefully repeat. And not just, random is not good, but even a simple attempt to order by time or by number is not good either. Here's a practical example in play. In Spark, we've run into situations where the same generated constructor accessor is generated 5,000 and more times, each in its own class loader. Fun. And because it's a reflection-generated class, each one of them ends up looking like that with a number. And just changing it to instead use a hash as a name makes them all repeat, and then we could log it and apply good profiles to them. Okay, that's a practical example, just happens in the wild in a real application people do run a lot. Okay, beyond these things, and here we're starting to get into things that are useful for some and maybe not others. So for example, if all we wanted to do is feed profiles in, that works to some degree. But what if we wanted to use those profiles to find actual pre-computed JITs so we don't have to compute them again? So profile matching is critical to be able to do good match rates, right? So we want to identify the same profile and match it and save ourselves the JIT work and get to fast code like that, right? No latency to the JIT, no CPU spent on the JIT, and do that for 2,500 methods, right? Right off the bat. Well, profiles are finicky because same profile to us doesn't mean, same blob. The profiles capture things like, branch prediction ratios and type profiles and things like that. And when we just have numbers, a tiny variation in a number is not the same unless we do something to normalize it or fuzzy up the matching or that kind of stuff. So those things are very important to be able to get good hit rates on things like compost hashes, because the profile coming in is going to vary in some tiny amount normally just out of natural variations. Class IDs are another example. And class IDs mean different things in different places, but I believe it's kind of all the same across the JDK. So class ID in one form or another will show up in optimized code in various places. Simple example is guarded inlining. So if this is of that class, do that, right? And if you've got a JIT output that does guarded inlining and it's checking if that thing is of that class, it's put code in there to do that. Now, you could do these nice abstractions that say, well, I'll link and resolve that on loading and all that, but that gets messy and gets in the way of various optimizations, especially since the IDs could be one of these things, as far as I know. For example, in HotSpot after Java 8, there's generally a class pointer into the metaspace. Is that going to be the same next run? Yeah, so we need some identification for it. Or it used to be a reference into the heap. Or in Zing, for example, we use numeric IDs. So we actually have just a number for each class, and that's what's sitting in the header. Fewer bits, faster access, that kind of stuff. One of the benefits of having numeric IDs is we can put all kinds of attempts together to repeat them. For example, Java line hash map. That should be number 23, right? We could try to do things like record the actual mappings or create hashes or ways to repeat them or that kind of stuff, because getting the same ID on the next run is useful. And also figuring how to resolve them back if you're not looking at numeric IDs is also useful. So those were kind of problems, and there's probably other classes you can think of from there, but I'm trying to kind of get in your head to think about run-to-run repeatability. Another thing is to think about the way you think about them. So correctness is actually not necessarily required, and trying too hard for correctness often hurts here. Because in general, we're talking about something, the JVM could start from scratch probably. So if the guess is wrong, you could probably correct it. For example, you might de-optimize, or you might just not match this thing. So if we don't get it right, then our hope is that all that happened is we lost some of the startup benefits. So we have motivation to make most of them match, but we don't have to be perfect. The issue to be careful of is sometimes you don't just lose the startup benefits, sometimes you lose a lot more. Because if you get it truly wrong, you may end up with just slow code that wouldn't have been that slow if you didn't try this thing. So you could introduce new ways of becoming slow. And the interesting thing is that an aggressive guess is often safer than a conservative one. Because an aggressive guess, when you get it wrong, is going to trigger. It's going to go away. It's going to de-op. We're going to figure out this thing isn't happening. But a conservative thing that's trying not to get it wrong will often end up with slower code than if you went aggressive. And since a lot of the speed we get in JVMs come from being aggressive and speculative, going conservative often loses those. So there's somewhat of a trade-off here. Because if you go too aggressive, then you're going to lose it too. So you got to find that middle ground between the two.